time thing. All right, so let's do this integral right here. Let's knock this one out. Let's do this one. This one is just a basic substitution, right? I had already wrote it on the board earlier. U was the bottom, du is exactly the top. So the antiderivative of this, no more integral sign, 1/8 natural log of u, but u is 4x squared minus 4x plus 3. And then I'll do a plus c at the very end. Plus, or let's make this minus, 1/2 integral 1 over 4x squared minus 4x plus 3 dx. So I actually took the antiderivative here. I'm done with that. No more work needs to be done. On this one, I pulled the -4 out, made it a -1/2, and I'm looking at this constant over an irreducible quadratic. Complete the square. Here we go. So I'm going to have to complete the square on this right here. Ready? Take a 4 out first, right? So you have to take a 4 out here. So I'm just going to do my scratch work over here on the side. Take a 4 out. I'm left with x squared minus x plus 3/4. Take the number in the middle, -1, half of it, right? -1/2, square it, 1/4. 1/4. So what I'm going to do here is have x squared minus x. I'm going to add a 4th and subtract a 4th. There's my hidden 0. I'm not showing you the work anymore. And then over here, plus 3/4. And that turns into, I'm leaving that there because that's the integral we're working on. Okay, so that turns into a 4 out here. These three, x minus 1/2 squared. And then these two, 2/4, 1/2, right? So plus 1/2, that. That's what this turns into. Yeah? What can I do with that 4 out here? Pull that out. It's on the bottom, so it'll become -1/8, right? So now I'm at -1/8. Integral 1 over, and then I pulled the 4 out, so x minus 1/2 squared plus 1/2, right? But you have to look at that 1/2. Like up to this point, this number out here has always been nice, hasn't it? Like 9 or 1 or 16, and everyone's like, oh yeah, if it's 16, then a is 4. If it's 9, then a is 3, right? But what if it's 1/2? Well, then it's just the square root of whatever the heck it is, right? Like, just like if it was 9, it was 3. Why? Because the square root of 9 is 3. If it was 16, it was 4. Why? Because square root of 16 is 4. If it's 1/2, then it's 1 over root 2, because the square root of a fraction is square root of top and bottom. Square root of 1 is 1. Square root of 2 is root 2. So a is actually 1 over root 2. Agreed? Does that look like something you can handle now?
Yes.
This looks a lot like 1 over u squared plus a squared. This is arctan, isn't it? All right, we're there. Do I have to worry about scaling anything? No, because this right here, that's my u. The derivative is just 1. So, okay, so I've got -1/8. That's coming from this part right here. Now, the formula for this. And a here is 1 over root 2, right? Okay, so the first part of the formula is 1 over a, isn't it? 1 over, no, you're looking at the wrong formula. This is a plus in here, right? It was a plus? So it is arctan, right? So the formula is 1 over a, which is 1 over this. What's 1 over this? Flip it over, just root 2. This is 1 over a. Arctangent of our u. What's our u? Our u is the x minus 1/2 over a, and a is 1 over root 2 plus c. If you give me that on the test, I'll be happy. Now, remember, there was another part of this answer, right? Like the final answer is that, don't tell me. It's 1/8. I think it was positive 1/8. Natural log 4x squared minus 4x plus 3. And then we have minus root 2 over 8 arctan of x minus a half over 1 over root 2 plus c. That's it. Check it. Okay. If you run into a linear expression over an irreducible quadratic, I recommend that you approach it that way. Let u be the bottom, take the derivative, try and match it. Okay? Like I said, there are other ways to do it, but in my experience, well, I just like hidden zeros, I guess. I'll be honest. I like hidden zeros. That's one of the more advanced thoughts in mathematics, believe it or not. Very, very tough theorems are proven by realizing hidden zeros in places. So it's a good exercise to see that. You can always put a 0 next to something, plus 0, plus 0. All right, let's look at number 8. Remember, these are all the preliminary concepts that we need before we attack this section. No, we haven't started partial fractions yet. That's why this section requires 2 days. Yeah. All right. What about this? We have a linear expression over an repeated irreducible quadratic. So x squared plus 1 is irreducible. You can't factor that, right? X squared plus 1. And it's repeated. And on top you have a linear expression. Play the same game. If you expanded it, then it would be exactly like number 7, right? Yes? But I'm not even going to play that game. I'm going to do this. I'm going to just go u is x. Well, no, I take that completely back, what I just said. It won't be exactly like number 7 because it'll be a 4th degree polynomial on the bottom, not a quadratic. Let's let u be the irreducible quadratic, just like we did in number 7, right? We let it be the bottom. So du would be 2x dx. That's what I would like to have there, right? Do I have that? No, I don't. Do I?
Still squared. The whole thing.
The bottom. Well, the bottom. This would be like u squared, wouldn't it? That's not quite du on top. So, is there anything you could do?
Force it to be a 2 like you did?
Could you force it to be a 2? All right, let's see what would happen. Let's just see if we tried the same thing. 2 over 2 here, and what would you get? So let's pass a 2 through. Leave a 1/2 outside. 2x plus 2 over what? X squared plus 1 squared dx. Now just split them right now. Just split them right now. You see? Just split them right now. If you split this, isn't this going to be the derivative is on top and u is on the bottom?
Yeah.
And then just split it. So you don't have to realize a hidden 0 here because you actually have what you need if you split it at this point. So take this, do 1/2 2x over x squared plus 1 squared dx. And then what about the other one?
It would just be 1 over u
Plus the 1/2. Again, right? The 1/2 goes there.
The 2.
And then the 2, it's going to cancel. I just didn't want to do it until after I.
That's cool right there.
Yes? This one, how can we do this one? U sub, right? U is this, du is right on top. So this one, can I just put a check mark without even doing it?
Yeah.
Okay. What about that,
That was
though?
like one of the ones we already did, right?
That's power.
Like above. And this,
Which one?
It's like, it was like
This one or that one?
That one. It's like number,
No. Well, I don't know.
1 over u squared.
Yeah, it's 1 over u squared. Yes, but our u is different. Up here it was linear, like this one right here. But it's the same concept. Do you see it's the same concept? What's in here is the u. If the derivative of it appears up top, then yes, it's the same exact thing. It's just our u is quadratic and the derivative is linear, so it works the same way. I want to know what we're going to do with this one over here. Pull this 2 out. Pull the 2 out, and that'll be a 1.
Whenever u squared.
Okay, hold on. Y'all are getting ahead of me here. Integral, pull the 2 out. I'm just looking at this one right now. Ooh. I heard u sub. I don't see du anywhere, though. Right? If I let u be the bottom, what's in the parentheses, then du's here. Pardon me? Trig sub. That's it. It's a trig sub. Good. But that's a weird trig sub. But do you understand why you can't do this?
Yes.
Right? Because it's not up there. And then it really falls into no other category. So what you're going to do is rewrite it now. It's 1 over the square root of x squared plus 1 to the to the 4th power. Isn't that what it means to square something? If you raise it to the 1/2, that's square root, right?
Yeah.
Take that and raise it to the 4th. You multiply these. Half of 4 is 2. So that is a hidden trig sub right there. You see it? What is the trig substitution that you use for x squared plus 1? What is it? X is a tangent theta. So a here is 1.
Yes.
The derivative of this is secant squared theta d theta. And the square root part of this will turn out to be secant theta. I'm not going to work through it, okay? But that's what it'll be. Then you just rewrite the integral. And we're almost done. So when I rewrite this integral, get integral 1 over, this square root thing is what? Secant theta, but then to the 4th, right? So secant to the 4th, theta, d theta? No. Secant squared, theta, d theta. Sorry. I'm just laughing at how fast this subject builds on itself. I mean, I forget what it's like to be on your side where you're learning this stuff for the first time, but even as an instructor, just how quickly this subject builds on itself is kind of mind-boggling. Because this is about to turn into cosine squared. And that's going to use a power reducing formula. That's going to be what we did a couple of days ago, right? Like not 4 weeks ago, like a couple of days ago. So this is going to turn into squared, right? 1 over secant squared, which is the same as cosine squared when you flip it. And so when you have an even power of cosine, then you use that formula, right? The half angle. So this becomes half comes out, and then you'll have 1 plus, who's got it? Cosine 2 theta. See, there's just no way you're going to be able to do this unless you're comfortable with the homework, right? I mean, you have to be comfortable with what you did in the homework. You have to have exposed yourself to this, or else I'm just sitting up here writing in hieroglyphics, basically.
Why wouldn't you use the other sign?
The other what?
The 1 minus sign, or the identity for cosine? Yeah.
Because if you turn this into 1 minus sine squared x, or sine squared theta, right?
Mm-hmm.
Then you still have to deal with sine squared.
Oh, okay.
So how are you going to deal with that? Well, you would use a formula.
So then you can
It's
do it
it's
individually
faster.
now? You
It's
do it
faster.
individually
Yeah, now we can do these individually. So what's the antiderivative
Theta.
of 1 is theta, right? Antiderivative of cosine 2 theta is
Negative sine.
one half sine 2 theta. And I had a half out there, didn't I? Let's see. Yeah.
The first.
Okay. We good? I'm going to keep going with this, but I want to kind of summarize where we are because I kind of lost track. All right. So let's just recall. We started. Yes.
Wouldn't you find theta?
Oh yeah. I'm not done.
Oh, okay.
I'm not done. This was the original problem, right? We got a little clever, and we were able to get it to be 1/2 integral 2x x squared plus 1 squared dx. And then the other one, plus integral 1 over x squared plus 1 squared dx, right? This one I put a check mark next to because we could do it. I want to do that real quick. Can we do that real quick? That's just, isn't this just 1 over u squared? The antiderivative of 1 over u squared would be negative, nope, careful. Negative u to the negative 1. So this is going to be, the antiderivative here is actually negative 1/2 u to the negative 1.
Yes. Right.
Okay, that's the antiderivative of this, plus c. And I'm working on this one right now, and I've gotten to this. This is where I am. So now I need to get this theta back to x. So what is the trig sub that we used?
Attention to that.
We had used that, what was it? X was tan theta.
That's exactly right.
And I can draw a triangle from this. Theta x1 root x squared plus 1.
And theta is the arc tan x.
So how do you, question, what? We okay with the triangle?
Right.
Okay, theta. How do we get theta? This is part of why I had you watch the videos, because I never did a problem in class where you had to solve for the theta. So all you do is what?
Arc tan.
Take arctangent, or arc, whatever the trig function is, take the inverse on both sides. So this is going to turn into 1/2 arctangent of x, that's how you get theta, plus 1/2, sine 2 theta. I did that on a video too. You can't do 2 theta because your triangle has theta, not 2 theta. So what? You break this down into 2 sine theta cosine theta using the trig identity. The 2 and the 1/2 will cancel. So I don't need that half. So it'll just be sine theta cosine theta. Sine theta is
1 over
x over root x squared plus 1 times cosine theta, which is 1 over square root x squared plus 1.
It's not a, there's no formula for cosine 2 theta, is there? Or is it the same?
Yes, there is. They're different ones, though. Yeah. All right. I can put these together because it's multiplication of 2 fractions. These 2 roots come together and just become x squared plus 1. No root. So the final result of this is equal to this, which I will write as negative 1 over 2 times x squared plus 1. That's the same as this. And then this right here, and I guess I'll pass a 1/2 through. I don't know. Plus 1/2 arctangent x. And then this half goes through to this one, right? On top I have x. So x over these two together, 2x squared plus 2, if you pass the 2 through both terms, plus c. Took a little while, didn't it? Let's see.
I have a question.
Yes, go ahead.
If you pass the 2 at the bottom of the first one,
Yes.
do you combine them?
Yeah, you could. You mean your first term and your last term? You could put like x minus 1 over 2x squared plus 2. Yes. So what I'm going to do here is I'm going to ask the computer to integrate that for me. I'm going to see if our answer looks anything like theirs. Not that I don't trust our answer, but I always feel better when the computer says that it agrees. X plus 1 over x squared plus 1, that quantity squared, dx. Yay for us. Yeah, that's it. Yay for us. That's it, right? They pulled a 1/2 out of everything. So that 2, bring it out. That 1/2, bring it out. This 2, bring it back out, right? So we have a 1/2 outside of everything. Who cares about the C? And then since these have the same denominators, put them together. And it's x minus 1 over that. And that's, I don't know why they always write it in their polynomials, they always write their polynomials in ascending order. You know how we always do polynomials descending order? In Mathematica, it always goes ascending. It has to do with the reason, like power series, we'll talk about later. But that's it, right? We're good? We happy? I shouldn't say are we happy. You understand? Okay. Yeah. Yeah, you do all that work, you forget the C, I'm going to take all the points off. All right. All of the problems that we just did leading up to what we're about to talk about, none of them required partial fraction decomposition. None of them did. And so the reason I'm showing you these as a preliminary is because I don't want you to see these types of problems and try and do partial fraction decomposition when you don't need to. All right? It's kind of like taking out a hammer to cut a piece of wood. You know, like you want to pull out the right tool for the job. You only use partial fractions when you have certain things in play. All right? And that's what we're going to talk about. When do you pull out this thing called partial fractions, and how does it work? So we first need to review briefly what a rational function is. A rational function is the ratio of two polynomial functions. And I gave you a bunch of examples here of rational functions. Do any of those problems, from what you can tell, do any of those, if I were to ask you to integrate any of those, do any of them look like what I just gave you? Like the preliminary stuff? No. They're all much more complicated, aren't they? But rational functions come into play a lot. And they're an important group of functions that come up in different sciences and different fields, rational functions. So we need to be able to integrate them. And how would you go about that? So let's pay attention to a couple of things here. On the f function, what is the degree of the numerator? 3. Degree of the denominator? 1. Okay, so the degree of the numerator is bigger than the denominator there, right? How about on g? Degree of numerator? 2. Denominator? Degree is 3. So there, the degree of the numerator is smaller than denominator. How about on h? 4 and 3, so degree of numerator is bigger than bottom, right? J, opposite, right? 2 and 3. What about K? Same degrees, right? Now that's important because when we try and integrate rational functions, the strategy that we're going to employ for these is to first inspect the degrees, all right? If the degree of the numerator is less than the degree of the denominator, we're just going to move on to doing what we're going to do. Okay, so if the top degree is smaller than the bottom, we're just going to go and do something. But if it's the other way, if the degree of the top is bigger or equal to, so if the degree of the numerator is greater than or equal to the degree of the denominator, we first must use long division. And then from there, we can do the rest. For what remains,
I see why you only put like 6 questions.
you see that? Yeah. For what remains after we do the long division or whatever, we have to use partial fraction decomposition, which was a topic that was covered in pre-calculus, hopefully covered in pre-calculus. And I understand that it's been a while, and I understand that you're going to need a refresher on it, but I think the best way to do it is to do it as we go, all right? So what we're going to do, here's all these notes, okay? And it makes no sense for me to sit here and talk about it right now. Let's just get into it by starting with this first one. I should have enough time to just do the first one, all right? A. Find the integral antiderivative x cubed plus x over x minus 1. All right. Is this a basic U sub? No. Is it integration by parts? Probably not. Is it like a trig integral, like cosine sine? No. Is it trig sub? I don't see trig sub right, I don't even see it hiding from me. Maybe, but nah. And it doesn't look like any of the preliminary ones, right? Like, does that look like any of the preliminary ones?
No.
The preliminary ones is like constant over linear, linear over irreducible quadratic. I don't see that. But it is a rational function. Polynomial divided by polynomial. The degree of the numerator is bigger than the degree of the denominator, right? Since the degree of the numerator is bigger than the denominator, we must start with long division. So this is the way long division goes. You go good old school division box, like this. On the inside of it goes the numerator, which would be x cubed plus x. But because we're doing long division, we need to account for any spaces that we have in the polynomial. And then on the outside, we put x minus 1. Then you say to yourself, how do I turn this into that? What do I have to multiply x by to turn it into x cubed? X squared. So right here above the x squared, I'm going to put x squared. And then you multiply x squared times x, which would give you x cubed. You put it right here. Then you do x squared times negative 1, and you put it under here, minus x squared. We good? Then you come through and do what? Subtract. So it changes the signs of what's there. So this becomes minus, this becomes plus, and then you add down. So the x cubes are going to go away, aren't they? How many x squareds am I going to have? Just one, so x squared. Anything else? An x comes down, right? And then 0, I don't really need to bring it. And then you play the game again. You say, what do I multiply x by? To turn it into x squared. X this time, right? So I put plus x. And then do the same thing. X times x, x squared. X times negative 1 is negative x, right? Yeah. And then come through, change the signs. You get 2x. Run out of room. You keep doing this until when?
The remainder?
When do I stop?
When you get a constant.
Yeah, when you get a constant.
When the power of this is bigger than the power of this, that's when you stop. Right now they're the same power, aren't they? So I can go again. What do I multiply x by to get 2x? 2. So plus 2. And I go through, and I'm out of room, I'm sorry, the camera will pick this up. Some of you in the room may not see this. 2x, so that's this, and then minus 2 goes next to it, and then I change the signs, and I'm left with 2, right? That's your remainder, right? So what do? We go back to elementary school and we put this? No, we don't do that. We don't do that. It's 2 over what we were dividing by, yes. You go plus 2 over what you were dividing by. Right, right. I'm going to see y'all do 3 divided by 4. I mean, think about that division symbol just for a second. What is it? It's just, yeah, it's like me drawing this with hey, that's a box up there. You put whatever you want in there and you put whatever. That's basically what that is. It's like the dots represent whatever you want them to be. What a terrible symbol. All right. I don't like it. All right, so what we've said is this. This expression is equivalent to this, right? I mean, that's what we're saying when we do division. If I say 12 divided by 5, I could rewrite that. Let me do this. 12, 5, it goes in there twice. 10, I get 2 remainder. So remainder 2. No, we don't do that. We go 2 plus 2/5. That's what that really means. So 2 plus 2/5 is the same as this. So it's the same expression, but it just looks different, right? But look at what we gain by this. Look at how great this is going to be for us. Integral, if that expression is that, are you going to be able to integrate that? With ease. With ease, right? Because you can now integrate term by term. Power rule. Power rule. Power rule. Constant over linear. We're in business. So we have an answer, right? I don't think we need to do any more work. We have 1/3 x cubed plus a half x squared plus 2x. Drum roll. Drum roll. 2. Good. It's all right. 2. Natural log. X minus 1 plus c. We're good. Okay. That's it.
That was partial fraction?
No. That was we were integrating a rational function. We noticed that the degree of the numerator was bigger than denominator. So we did long division. When we did that, everything turned out to be something we could integrate, and we were happy. It's not. See, what's going to happen next class is that when we go through this step and we get this, some of it will be nice. It'll be nice, 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 and we'll look at that and go, oh, crap. And there might be more. And then we have to do the partial fractions to try and break it apart. And so we haven't seen partial fractions. We will lead perfectly into next class, right into partial fractions. So all the groundwork is laid. Make sure you're caught up in 6.2. Man, I would have to go pick exactly what problems you could do. Who has the book? I could tell you right now. What's the assignment? Is there an assignment at the end of this? No? Yeah, we're just going to talk about it. I'm not even going to test you on it.
So the next test is going to cover partial fractions and fixed sub and integral?
Yeah. I'm going to do 6-2 all over again. Maybe when I get home. 6-2.
There's really not much you can do. Hold on a second. Hold on.
Are there any problems
So how am I going to know if my answers are right?
Are there any problems like that one, the example you just did, like the x plus 1 over x squared plus 1 squared?
The what?
Like that problem we just did that took like
Oh, that took a while?
an hour?
What about it?
Is there any problems like that we could practice on?
Yeah, I can try and find something. Let me look in the book. Let me just say for homework though, make sure you're completely caught up on 6.2. Make sure everything's good there. If you have nothing to do, then go review partial fractions. You know, just go look it up, Google it, like how to do partial fractions. All right? You can watch some older videos. I don't know if I have anything for partial fractions. I mean, I do Cal 2 videos, but I don't have any videos dedicated just to partial fractions. But you, yeah, nah, I wouldn't mess with that. Yeah.
I was trying to find partial fractions.
No. Okay, let me turn my camera off and I'll see if I can find something for it.
So our next step is going to be over just the rest of the integration?
And we have the rest of chapter 6. We have to figure out what the numbers mean on top and bottom.